Everyone. My name is Khen. I'm a PhD candidate in the Ergodic group in Tel Aviv University. Thank you for the opportunity to give a talk here. And today I'm going to talk about diagnostic phase transition and the connection to boson sampling. I will explain in a minute. Okay, so I will briefly describe say a few words about phase transition and the motivation for the project, and then I will discuss a little bit about boson sampling and Gaussian boson sampling, which is another variation of boson sampling. And I will cover three projects that we are working on. The first one is multi-body localization and ergodic phase transition with Lanchas coefficient. The second one is using the same setup in boson sampling. And the third project is about chaos and the integrable phase transition in boson sampler. And then I will sum up. Okay, so yes, okay. So the phase transition is something that I guess almost everyone here knows about. So phase transition is something that we are familiar from day to day because we see it, but we see a lot of classical phase transition, which is most of the time is connected to some thermal fluctuations. But today I'm not talking about classical phase transition, I'm talking about quantum phase transition, which is a little bit different. Quantum phase transition are phase transitions that are driven by the quantum fluctuations and not by any thermal effects. Actually, it occurs at absolute zero temperature. There are several examples of quantum phase transition, and there are more. The superconductivity, localization, and other things. And the motivation to study it is because it gives us some fundamental understanding. It gives us some emergence of geophysics and potential technological applications. And a few words about localization, which is the one that we will a little bit more focus on here. So localization, it basically says that if a system, we will, okay, so I will give a few words about it later. Okay, so what is a boson sampler? A boson sampler is a method, it's a non-universal quantum computer. Okay, it's a way to calculate some things leveraging some properties of quantum mechanics. And it shows a quantum advantage. I added the question mark because it's debatable whether it gives a quantum advantage and in what manner, because basically I mean, theoretically it's a sharp P problem, so it's considered very difficult. A computer that calculates very difficult problems, but it's very limited. Basically, it calculates permanence, which is basically a combinatorial problem. The reason that there is some debate around it is because there are some. First of all, it's very limited. I mean, the number of applications to use a boson sampler is very limited. So there are some people that say this is like a toy just to show advantage, but it's not practical. This is the first thing. And the second thing is there's some evidence that the noise might be a very, constitute a very significant problem when we scale. So it's not clear if it's usable. However, we show, in a minute I'll show you, one application that no one has suggested before, and then we think that we could use a boson sampling, just a tiny lab to study about phase transitions. I added also some experimental progress and the status of the current research. Okay, so the first project is about the many-body localization and ergodic phases. What is many-body localization? It's a generalization of understand localization. Basically, there are some systems that thermalize, and if we have a isolated system that thermalize, so all the it explores all the microstates accessible during the evolution. This is the ergodic phase. However, there are some systems which fails to thermalize, fails to explore the entire phase space. These are And for these systems, we say it is localized. So they remember the initial states. This is the one significant difference from ergodic systems. So we suggest in this project, and I will not cover all the details, but just give you the highlights. So in this project, we suggest a new measure, a new way to diagnose this phase transition. And what we use is a power law random banded matrix model. It's some matrix model that people have explored, have used in order to study and to model this phase transition. Basically, we have an Hamiltonian, and then we build what is known as creel of basis. We just use some iterative, we start from initial state, and then we use some iteration procedure. And then we just multiply the first time by the Hamiltonian, the second time, and so on. And then we end up with some basis, which is known as the creel of basis. And then when we do just some diagonalization of this new set of vectors, we can represent the new Hamiltonian in this new basis as a three-diagonal matrix. This three-diagonal matrix has some coefficient, and the diagonal is less relevant. The most important one are this Bn's coefficient, which is known as the Lanchas coefficient. So this Lanchas coefficient, our suggestion is to use them to give them some interpretation of probability distribution. So they are always positive, and to give just we suggested a normalization that give them such an interpretation. So once we normalize them, we get some plots that gives us for different mu values. Mu is just a parameter of the model. Different plots of these Lanchas coefficients. So the model that we used to model the phase transition, as I mentioned, is parameterized by this mu parameter, and mu parameter has a phase transition exactly at 1. Okay, so for lower than 1, we are in the ergodic phase, and higher than 1 is in the localized. So what we saw is that actually using this interpretation, it's possible to take some quantities, asking some questions about the quantities of this probability distribution. For example, we could ask about the moments of this probability distribution, or the entropy, the Renyi entropy or Shannon entropy. And then we see a distinct transition between the two phases. And what is nice that we see clearly that for larger mu larger than 1, which is the localization regime, the initial state, the system remembers the initial state. However, in the ergodic phase, it's not the case. So it forgets the initial state. Okay. So the boson sampling, as I said, is a method to calculate some permanence. We can think about it as a circuit, as just a unitary, and then we inject some photons to the unitary, and then it calculates some permanent of submatrices, some minors of this matrix. And this is, and it looks like this. And calculating the permanent is something very, very difficult in general. But we wondered maybe using this machine in order to get to and parameterize the circuit in some parameter that we control and describe some properties of the system. For example, phase transition between ergodic and MBL is something that we will see in the probability distribution when we measure the output states. So basically, we inject photons in the circuit, and then we measure the output probability distribution, and then we ask the same question. I mean, using the same logic as the previous project. So the strategy was as follows. We start by some Hamiltonian with some model, for example, the one that we used previously. And then, because actually the circuit is a unitary, we just use some exponential map, and they get the unitary. And then we need to project into the circuit. This stage is not is not necessary. We did it because we wanted to test it on a real quantum computer. So we worked with Quantum Machine Company, and they run an Orca device, which is limited in the structure just to be some diagonal shape like this. So we need to somehow project our general unitary into this shape. So we did some technical things to make it, to project it into this form. Then we inject some photons, 2 or 3 photons inputs to the circuit. For example, here you can see the second and the third and the fourth modes. And then they somehow blend up, and then we get some probability distribution in the output modes. We collect the probability distribution, and then we evaluate the properties of this probability distribution. This is the strategy. So in the left, we can see, the most important curves here are the first, the orange, which is the simulator. This shows the phase transition around mu. There's a mathematical simulation of the Orga device, and here the experiment. They show similar trend. However, we suffered from a very significant noise. It's for some. In some cases, it's up to 50% noise, very noisy. So it's quite impressive that it still shows a reasonable result. But we are doing another experiment these days in order to get better results. Okay, and the third project is somehow related, is about diagnostic quantum chaos and integrable systems. Integrable systems are systems with most of the time high symmetry and a lot of conserved quantities, such that we can precisely solve it and know the dynamic. However, in chaotic systems, it's not the case. It's very sensitive to initial states, and quantum chaos is a very active field of research these days. And the idea is to try to see whether we can detect this as well in a boson sampler. So we use some random matrix theory model, which give us some way to, again, parameterize this transition. This is known as a Chavda model, someone that have already suggested this model. And these matrices are just a GOE matrix, a Gaussian orthogonal ensemble, and the Poisson matrix, which is just a diagonal matrix. Both of them are random variables. And this transition can model the transition between a chaotic regime and integrable regime, parameterized by this lambda. There are several signatures of chaos, of quantum chaos. There is no consensus about a single one, which is the correct one. There are several suggestions and connections between them. I will not go over them, but there is a very famous Wigner-Sommer's characteristic, which says that a GOE, or in chaotic systems, there is a level repulsion. So the probability of getting the distance between two energy levels the probability goes to 0. Yes, and there is another one that I will just mention. It is the out-of-time correlation, which is another theoretically suggested way to measure the information scrambling of this of the system. And then we found that someone have actually suggested something very close. Victor Batista have always suggested a way to connect between boson sampling and to what is known as the Kick-Trotter model, which is another model to diagnose and to model chaotic quantum chaos. It's just a sequence of, it's just a Hamiltonian, which is time dependent and periodically gets kicked. And it's parameterized by K, which describes the strength of the kick. For very weak kicks, it's integrable, and for stronger one, it becomes chaotic. So this guy have shown that actually measuring the output probability distribution for this specific Hamiltonian has a direct connection to the OTOC, or the OTOC, which has been adopted as one of the leading signature of chaos. And then, so it gives us another theoretical justification for our hypothesis that maybe diagnostic of phase transition, such as chaos and the integrable, has something to do with the boson sampler. This is a work in progress that we are working with the group in Paderborn in Germany, and we soon will have enough results to publish. Yeah, so there are a few efforts that we are still working on. The first one is to unify and to make the connection between the Lanczos coefficient and the distribution of the Lanczos coefficient and the distribution of the output from the boson sampling. It's not clear, the mapping between them. Both of them shows some transitions, but it's not clear. I mean, there are some hints that some connection must be there, but we are still don't know that. We'll work to improve the experimental results. There are some first theoretical question about fundamental connection between phase transition and boson sampling. Is this procedure of boson sampling, which somehow blends all the information, all the photons, and making some interaction and gets permanent, this combinatorial things has something to do inherently, something deep, which is connected to the phase transition. What type of phase transition can be detected by boson sampling? And what about Gaussian boson sampling? Gaussian boson sampling, I just mentioned it here. We are not, I mean, Gaussian boson sampling is not using single photons or Fock states, it's by using squeeze states. And then you don't get the permanence, you get Hafnians, which is something close, but it's not exactly the same. So, and the one great advantage about Gaussian boson sampling is that it's easier to produce and to realize in experiments. So people know how to do it for a large number of modes, and it's not clear for us if it still could work. Yeah, that's it. Is non-degenerate? Non-degenerate? Yeah. No, actually, we assume, okay, the Hamiltonian is, okay, I will show you. Oops. Okay, if we have an assumption about the non-degeneracy, well, basically we defined it based on the GOE matrices. So it's with zero probability be degenerate, right? If it's a must condition, I'm not sure about that. Basically, what we do, we sample a GOE, just Gaussian independent values, and then we multiply by some matrix that depends on the distance between the two indices. I mean, some off-diagonal matrix. I mean, this is the paper, but they can, yeah.
Okay, yeah, I'm just asking because it seems that you wouldn't get the basis if it's degenerate.
So maybe, yeah, maybe it's the case. I mean, yeah, we don't encounter this problem here, but maybe you are right that this is one of the reasons, yeah. So when we got this Lanczos coefficient and we normalized them, I mean, they had no, we gave them interpretation of, okay, to be honest, some previous literature gave some interpretation that gives some connections to probability to jumping around or moving between states. But we formally did it. We formally normalized them and give them. So to answer your question is once you normalize this coefficient and see them as a probability density distribution, we could ask question about the moments or the entropy of the distribution, right? The Shannon entropy or the Renyi entropy. So this is the step that we have done. And this one this step revealed the transition very clearly.
So you didn't mention, but how does this compare to other indicators of this transition? And maybe you can comment about the fact that now there are doubts whether there is a transition at all. And,
Okay, there are some previous works that worked on the same band matrix models, and they show the transition on the same value, and we were perfectly aligned with some findings. About the second thing, I don't know. I don't know what to say, that maybe there is no transition at all about this.
yeah, there is some statement that there are small, like rare inclusions in a system. I don't know which dimension is this. This is a many-body localization in 1D?
Yeah, so no, I think it's 2D.
2D.
As far as I remember, yeah. I mean, it's matrix model, yeah. But I will make sure, yeah.
Then in 2D, for example, the claim is that there is no transition. You have these small thermal inclusions. They're rare.
Mm-hmm.
I don't know. I'm just.
Okay.
You're saying it aligns with other measures.
Okay. Yeah.